Hi guys, in this video, I return to the fundamentals of electronics, and the first lesson is the half-wave rectifier circuit. Before delving into the half-wave rectifier circuit, let's first discuss the transformer. A transformer converts a sine wave voltage from the primary side to a sine wave voltage on the secondary side, effectively transforming AC voltage to another AC voltage, such as from 240 volts to 15 volts. What happens if I connect a resistive load to the secondary side? Because the current can flow through the resistor in both directions, resulting in a sine wave voltage across the load. Next, we introduce a diode to the secondary side. Since the diode allows current to flow in only one direction, let's analyze each half wave. It becomes forward biased during the positive half wave, allowing current to flow to the load. Conversely, the diode is reverse biased during the negative half wave, blocking current flow. This results in a positive half-cycle voltage across the load. It is the construction of a half-wave rectifier circuit. It converts AC voltage to DC voltage. The value of output voltage is calculated using the following formula. If the input voltage is 15 volts and the voltage drop on the diode is 0.5 volts, the output voltage is around 6.5 volts. What happens if a diode is connected like this? If the diode is connected in reverse, it becomes reverse biased during the positive half cycle and forward biased during the negative half cycle, resulting in a negative half cycle voltage across the load. Returning to our circuit, although the output voltage is DC, it is not smooth. This is a big problem with many circuits, IC or MCU. To achieve a smoother output, a capacitor can be added to the circuit. Let's analyze this. When the capacitor is connected behind the diode, the rectified current charges it, causing the capacitor voltage to rise to the peak voltage. At this point, the diode becomes reverse biased, blocking current flow. If the output is not connected to the load, the value of the output voltage is the peak voltage. It is calculated by the following formula. When the load is connected to the output, the current of the capacitor is discharged from peak voltage into the load until it is recharged in the next cycle. This process keeps repeating. As you see, the capacitor's charging time is a quarter of a cycle, while the discharging time occupies the remaining cycle duration. Consequently, the capacitor discharges most of the time, resulting in a high ripple voltage. To reduce ripple voltage, increasing the capacitor's capacitance is an option. However, as the load current increases, the ripple voltage also increases due to the capacitor discharging more. In practice, using numerous capacitors is impractical due to PCB size limitations and cost constraints. Thus, a more effective solution is required, which we will analyze in the next video. In conclusion, the half-wave rectifier circuit is best suited for applications requiring simple, very low current, low efficiency. In the remainder of this video, we will conduct experiments to evaluate how the theory aligns with reality. In the initial experiment, I examined the input and output waveforms. The resulting output voltage displayed a positive half cycle of a sine wave. Next, I use a digital multimeter to measure the input and output voltages. You can refer back to the video for details on how the output voltage is calculated. The diode used in this experiment is a 1U407, which has a voltage drop of approximately 0.6 volts. Subsequently, I disconnect the load and connect a capacitor to the output. As the capacitor does not discharge, the output voltage transitions to a smooth DC. When the load is connected to the output, the capacitor discharges, resulting in ripple voltage on the waveform. The ripple increases with a higher load as the capacitor discharges more rapidly. Increasing the capacitance is one potential solution to minimize this effect.